Miguel Hernandez. And we have 1 hour and a half, and we have 6 presentations, so it's going to be 15 minutes per presenter. I hope, as we would like to give a couple of minutes for any question, I would thank you if you could do the presentation in 13 minutes or so. I will tell you when it is 13 minutes, so you should be finishing, okay? Anyway, if you are close to 15 minutes, I will stop you. So please get in time, because we are in a schedule. Okay, so we are going to start with Professor Panayiotis Frangos with the presentation See State Characterization using Experimental One-Dimensional Radar Signatures and Fractal Techniques from Georgios, Pouraimis, Apostolos, Kotopoulis, Basil, Massinas, and Panayiotis Frangos, who is going to be presenting. So Panayiotis, when you want, you
can...
Yes,
thank you very much. Thank you, Roberto. Thank you. I'm putting the share screen. Yes. One second. Yes.
Mm-hmm.
Just 1 second to put it full screen, Alberto. Yeah. Alberto, can you see it? Okay, full screen.
Yes.
Okay.
Everything.
Thank you very much.
When you want.
Thank you very much. Yeah. So good morning, dear colleagues. Good morning to everybody, and have a fruitful conference. I have about, as Alberto, about 13 minutes to briefly describe you a piece of research work that we're doing at our School of Electrical and Computer Engineering at the National Technical University of Athens, Greece, along with Georgios Pouraimis, who is a postdoc in our laboratory, and Apostolos Kotopoulis and Basil, who are PhD students in our laboratory, which is radar and applied electromagnetism laboratory. So the title of this piece of work that I'm going to briefly describe to you is C state characterization using experimental one-dimensional radar signature and fractal techniques. We have the Norwegian Research Institute FFI at Oslo had the kindness to provide us some real experimental data from radar data from helicopter. Actually, it was a PICOSAR, small synthetic aperture radar on helicopter, and this was and this was an experimental study of sea clutter, of sea state in sea clutter, which took place, as you can see, in 2014 in south of Italy, Taranto, sea of south of Italy, in September 2014. So the experiment took place in this particular experiment of sea clutter analysis. It took place in 2 subsequent days, 23 of September 2014 and 24, as you can see, 24 of September 2014. The first day, the sea was in the first day the sea was turbulent, and then the second sea the weather changed very rapidly, and we had calm sea, so it was appropriately chosen so that we have the turbulence in the first day and the calm sea in the second day. And here I will show on the left some particular specifications of radar collections, but I don't have the time to go in technical details regarding, for example, the beam width of the antenna. And the experiment was about 5 minutes or 10 minutes each day. I'm sorry. I'm sorry. Each day. And the grazing angle was in both days was about, as you can see on the left, from about 4 degrees to 54 degrees grazing angle. When I talk about grazing angle, is the angle between the horizontal sea surface and the direction of propagation of the electromagnetic waves. This is called in the radar technology the grazing angle between the direction of propagation of the radar waves and the horizontal sea surface. The FFI Institute was so kind enough to provide us this data during a NATO collaborative working group, which still continues. And we still continue to analyze this data. So, for example, in this transparency, I show to you on the left examples of radar range profiles. Once again, this is a picosar, small synthetic aperture radar, and on the left you see range profiles as a function of time. So this is the signal as a function of time. For example, on the bottom and the left, you can see a calm sea, representative calm sea range profile, and above it, a turbulent sea range profile as representatives. And you can see this is for angles for grazing angle equals to 20 degrees, for example. So, by the way, very shortly, this paper is 1D. Let's say we're making 1D mathematical analysis, range profiles with the signal, the return signal as a function of time. And now we moved our research already moved to let's say 2D or 3D in case. So we're looking all the data because in the SAR you collect a set of data, a set of course of range profiles, say 5,000 range profiles in this experiment. As the helicopter moves up, I forgot to mention that the helicopter moves downstairs. So we observe the sea for different grazing angles. So now we progress these ideas, and we observed in all these hills 3D functions, f of x and y, which are the raw data of the radar. And we're looking now at this direction of research. So, but this is still in this presentation we will see one-dimensional functions, range profile, signal as a function of time on the left, and on the right is the fast Fourier transform of this, which is the power spectrum S of f. Okay, the signal as a function of frequency, turbulent sea and calm sea. Okay, now I'm not going to go into details of the analyzing of this signal. We had some difficulties because the data were not provided by us. So we had to guess what it's about and to be in touch with the Norwegians to ask some questions. What is about? What is the full information about this data? But okay, I'm not going to analyze this too much. Also, we have had a simulation tool which was produced by our group about 4 or 5 years ago, and we're now also in the process to compare these results with a simulation tool produced by ourselves. In any case, I continue with my presentation. Here we applied some criteria to establish the sea state characterization. For example, we are used to fractal mathematics, and to calculate the following quantities: the fractal length of the range profile and the fractal dimension of the range profile. This is well-known techniques in mathematics to calculate the length and the fractal dimension of a anomalous curve. So on the left, okay, I'll explain. By the way, take into consideration that here we're using normalized range profiles from 0 to 1. So we normalize the range profiles obtained by picosar from 0 to 1. So this is a challenging problem because in this case there is no information about the signal strength. So this is most if you can characterize the sea state from normalized range profiles, this is even better from practical point of view. On the left, you can see particular range profiles, and also you see up and below it something called the upper blanket or the lower blanket, or the upper curve or in the lower curve. Blanket is used in 3D. Here is the curve, the upper blanket or the lower curve. This is one of the methods to calculate the fractal length of the anomalous curve, which is calculated as the ratio of the area between the upper curve and the lower curve divided by the height of it, 2 delta, which is the height of it. So let me proceed. This is done for several iterations, delta or epsilon. I'm not going to go into these details. This is one standard method to calculate fractal length, the fractal dimension. For example, here we show a simulated curve, and to show the accuracy of our algorithm. So here you have a simulated curve, as you can see, the upper blanket of it, the upper curve of it, and the lower curve of it, and without going to details on this difficult mathematics, you can see on the equation the upper curve and the lower curve selected in a particular way in the paper by Peleg for fractal analysis, and the delta or epsilon is the iteration, or in the iteration. And on the right, you can see the fractal length as a function of iteration, and let's say the derivative, of this curve of the fractal length is the fractal dimension as a function of iteration, and this is a characteristic curve for characterizing the surface or the line in fractal analysis. Okay, so here are the equations. Oh, my time is very limited. So here are the mathematics of it. You can see, as I told you, the area of the strip between upper and lower curve, the area, and if we divide this actually by 2 delta, as shown in the second equation, in a variant of this equation, we calculate the length, the fractal length, as a ratio of the fractal strip, of the area of the strip, divided by the height of this strip. L of epsilon is the fractal length as a function of iteration, and the fractal dimension is calculated after that from the fractal length. So unfortunately, don't have the time to analyze this in detail. So let me try to conclude. Here we have some results, and fractal dimension is a function of iteration. This is called a characteristic. I'm sorry. This is a characteristic curve. Sorry. And the interesting thing is for all angle of incidence. For example, this is shown for 10 degrees angle of incidence and grazing angle in the 25 degrees. 25 degrees grazing angle, and in all cases, the fractal dimension of the turbulent sea had the higher fractal dimension. So we, in all cases, for all data that we analyzed, and we calculated the ratio of this, which is called the sea state index, as we can see in the table, for different grazing angles, and we can see continuously SSI index larger than 1. The same happens for fractal length, as you can see. Only for the first iterations we have, but in all the other cases, the fractal length of the turbulent sea is higher, and the sea state index and so on. In addition to that, because my limit is very strict, my time is very limited, we have the variance of these curves, and we had a similarly very promising results for the variance of the range profiles. Finally, as a fourth criterion, we used a criterion usually used in C clutter analysis in the literature. So here we have the power spectrum density, power, return power as a function of frequency. And for lower frequencies, you can see that actually the least square curve, which is the dotted line for turbulent C, which is the dotted line, is always higher than the slope of the least square approximation, which corresponds to the calm C. So concluding and finally make the final remarks on it, we have a summary of how to present it. And now is very important is our plan of our current and near future research, which is regarding the 2D analysis that I presented here. We have comparison between the experimental data, experimental results, and simulated results that we have already developed 4 years ago, an electromagnetic tool for this. And also, as I told you already, we are already doing 3D analysis on the full data, full set of range profiles, which might have some advantages and disadvantages, also by using fractal advanced mathematical techniques. Also, we're looking at the spectra, because also the spectra of these range profiles, because already the Norwegians made some preliminary analysis and showed that for calm C, and I'm finishing with that, the calm C, the spectra appear to be more uniform in their report. Okay, and also perhaps this can in the future can be done for also terrain characterization. Okay, so I have some references here. For example, Mandelbrot for fractals, some old works of our, with Dr. Malamu and Kotopoulis and Pouraimis for fractal analysis and so on. And also number 6 is my professor advisor at the University of Pennsylvania, which was expert in fractal mathematics, fractal electrodynamics, and papers for document analysis by using fractal techniques. And many, Perizzi is a famous, a very good Italian professor in also in radar and fractal analysis and other. So, yeah. Yes, I'm sorry, yes. So yes. Finishing, we're still working. Thank you, Alberto. We were still working on this. It is not finished. We were already progressing on this, and we hope that we have better and better results on this difficult problem of C clutter analysis. So, Alberto, that's it. So, if you have any questions, please feel free.
Thank you very much. Just in time. Thank you very much.
Thank you so much. Thank you so much. Thank you so much.
Thank you very much. Very interesting, as always, Panos. We will have time for a very fast question, if any. Okay, no?
I have a question.
Yes. Yes.
Okay. Once I have been doing this how things, and we use this box counting dimensions calculations. Is it any relationship with your method?
Once again, here in this presentation, we used the experimental radar data provided to us by FFI in Oslo, and we used a particular fractal dimension method, which we called MFS or blanket method. MFS means modified fractal signature method. So in this stage, we establish we try to establish a clear distinguishing between turbulent C and calm C, and we're in progress to compare these results with simulated data which are produced by our own electromagnetic code. So up to now, there is still not a clear comparison with other methods, but we are doing this now, currently, comparing this criteria with simulated data obtained by our and using our own code, a computer code for this problem.
Okay.
Okay, thank you.
Thank you very much. I think this is it. Panayiotis, thank you very much for your presentation.
Thank you so much.
We are going to move to the next one. Next one is titled is Development of Georeferenced 3D point cloud of in GPS denied environments using backpack laser scanning system. with Dr. Syed Riaz as the presenter. So, Doctor, thank you very much for coming, and your time is starting now. You have 13 to 14 minutes and then one fast question, okay?
Thank you so much, Dr. Alberto.
Thank you.
Okay, so my presentation is visible to you?
Yeah.
Okay, thank you. So this is actually, good morning, everyone. This is actually a funded project to develop 3D models of the indoor environment where GPS signals are not available. And I'm thankful for my co-authors and co-researchers who worked with me to finish this task. So technically, what is the nature of this work? We are using 2D laser scanners. We are joining them in different orientation. And then we are making maps of indoor places, indoor areas. And then we are converting those information into georeferenced signals, means we are converting those information into lat-long information. So why we are choosing our 2D laser scanners? Because actually they are available from different companies. They are now they are giving very nice features of the environment, and they are having a lot of different ranges available. So this is for just explaining that how they are working. This is the slide which you are watching here, that they are actually taking a slice of the information of their surrounding. And if there is some obstacle available, so they can inform you that there are some specific walls, specific objects present in their vicinity. So if, for example, I'm holding this sensor and I'm moving in some room, some indoor place, and I'm just taking scans on different locations. So you can see that I can just accumulate all the scans and I can make some 2D map, just like here you can see from the blue line. And then this is the information of that floor where I'm moving. Now, if I'm needing some map for 3D information, so I need another sensor. So in this work, we have combined more than one scanners. As you can see that this is the horizontal one, which is responsible to calculate 2D map. And then we are connecting one orthogonal sensor here, and it is now detecting the Z axis of the area. So now technically we are now having all three axis information, X, Y, and Z. And then we can combine this information to construct the map of this area. So this is one example which I have just placed here, that we have taken this experiment in some indoor place, and then this is the constructed 3D point cloud of that area, and you can see that we are having X, Y, and Z information generating from this method. There are different kinds of platforms available. For example, there are some handheld system on the left-hand side. You can see there are some trolley-based systems or some backpack systems. So in this work, we have chosen backpack system because this is comparatively easy to hold. And you can see that we have now 3 scanners on different orthogonal orientation, and we are having this physical implementation of this particular mechanical design. And then the surveyor is just holding that backpack and moving in that area where you need to make map of that environment. Technically, there are, if you see, there are some local references available for every sensor. So we are converting all local sensors data into the main horizontal scanner data. And when the person is moving, so actually we are combining all that data with respect to this horizontal scanner. This is the instrumentation block diagram for all the system. So we can divide in 2 steps. First is that when the person is carrying the backpack and doing surveying of some area, so we are calling that thing that this is the online step, as you can see here. So during this step, we are collecting all the scanners data, and we are using ROS based information collection system, and all the data has been taken in a ROS laptop. And then we are, during this process, we are running a library, which is a Hector Slam library, to compute the pose of that surveyor and the 2D map of that area. Then we are just collecting this information and storing during this surveying operation. And then we are switching to our offline step. And during that offline step, we have used MATLAB scripts to make first registration of all the scan which we have collected from different scanners. And then we are registering this information on our global frame. And then we extract the building planes. For example, if you would like to extract building information of walls, pillars, and some other objects present. And finally, we are going to transfer this information into georeferenced coordinate system. So technically, mathematics, I'm just summarizing the mathematical steps. So the Hector Slam is running on the ROS node, which is running the probabilistic computation for estimating the map and 2D pose of the surveyor. And then when we are having this information, we are just transforming the other two scanners information on the local reference of our horizontal scanner, which is indicating by the equation number 2. Now, by combining all the scans which are now available from all scanners, we are now having a single complete scan of the environment. And then we are converting that scan into world reference based on the pose estimation which we have received. So this is one example when we would like to make the indoor model, indoor map of some environment. So for example, this is the corridor of my campus, and you can see that I'm holding this backpack system and I'm moving in this corridor. And by moving in this corridor, on the right hand side, you can see that this is the developed 2D pose, which is indicating by the red points. And on the with the cyan color, you can see that this is the 2D floor plan of that corridor. And after registering all the scan data during this process, you can watch that now I'm having 3D model of this corridor. And important thing, if you can see that all the information which is available, for example, vegetation information, for example, pillar information, from, for example, some civil structure information, we can gather from this 3D model of this environment. And because we are using 30-meter Hokuyu scanner, so that's why you can see that we are having on the left-hand side and right-hand side, we are having approximately 25-meter information. So if you are having some more greater range scanners available, so you can construct with more detailed information in greater ranges. And after that, as I'm telling to you that when we have constructed this this 3 XYZ information, which is right now in meter. So now we need to convert this information into lat-long information. And as you can see that this place is not having GPS signal. So we are now needing some conversion of this meter information towards the lat-long information. So we have done a very simple step that we have find out some closest area where we can find the reference GPS locations where we are getting some GPS signals. So you can see from A and B, we are getting some values of GPS signal available. This is actually the campus road. And then we are taking midpoint of that campus road and just making one orthogonal projection of that area towards the area where we have moved. So you can see that this is the red area where we have moved, and here we are not finding the GPS updates available. So after that, we are having some small trigonometric operations. We just convert using some trigonometric operation. We have computed dy and dx, and we converted that lat-long information into the meter information. And as you are watching that, this area is not so much long, so we are just using some specific conversion. We are not using a proper equation which is complete, which is a little bit more complex to convert meter information into lat-long information. So after that, if you see that same area is now converted into lat-long operation, and you can see that now we can represent this indoor place with respect to lat-long operation. And actually this is the task which is given to us by different local companies, because they would like to actually model buildings having multiple floors, and they are having multiple offices. So they would like to target them with respect to lat-long operations. So that's why we did this job, and we just delivered this unit to them. And there are some more results. For example, we have taken another corridor, and you can see that this corridor is comparatively more longer than the previous one. And this is the 2D map which we have constructed. And after that, this is the 3D model in terms of lat-long operation. And you can see again that there are a lot of information available with respect to vegetation, with respect to civil structures and some other minute information. And then we have visited one construction site. You can see that on left-hand side picture that there are some construction work was undergoing in that area. And during this particular scenario, we have taken again our surveying job, and we provided this result in terms of lat-long operation. So technically, we have converted all the information which is available in that area in terms of our georeferenced locations. So this system is working very nicely, and we are satisfied with the performance. And when we have compared the results with the ground truth, so 99% accuracy we have found, and there are some minute errors which we have find out, and we are also focusing to remove them. And the important thing which is I would like to share is that the time taken to develop all this method is very, very small. If, for example, some other method of measuring or developing these kind of maps, if someone is taking place, for example, some manual measuring techniques or some stationary scanning based techniques. So this moving system is working very nicely and very rapidly and developing all this information. And in future work, we are targeting also to make addition of some vision information to colorize this information in order to make more better map representations. So many thanks. And if you are having any questions, please, and any suggestions.
Okay, thank you very much for the presentation. It was perfect timing, so thank you very much. And very interesting. Is there any question in the audience? If no, we have time for...
Yes, I have one, if you don't mind. A question about the scanners that you use, the lasers that you used are, can you tell us what the wavelengths are using this type of lasers? And if you use them in continuous wave or in the pulse mode?
Actually, these laser scanners, I'm right now not remembering the correct wavelength, but they are all in those regions which we can use in indoor environments. For example, they are following all safety standards. So I think class 1, they are called actually class 1 laser scanners. So for us, actually, what we are needing, we are just needing that they at least cover 30-meter range, which they are covering. And they should work in that area where some pets or maybe humans, they are available in that region. So that's why we just picked that particular laser scanner.
Okay, okay, thank you very much. Because I was interested in the power that they deliver because of the safety of the people who are, okay.
Yeah, this is they are safe. They are class 1 standard.
Thank you very much.
Alberto, if you permit me a very short remark, it's Panayiotis. Yes, very short remark. Okay, by the way, I just remembered in the area of radar that I have been working for many years, we are using 3D laser scanning for example, for making the 3D CAD model of, for example, of trucks or for cars or other objects. And because they make experiments, radar experiments for experimental data and simulated data, and they are needing these 3D CAD models of trucks or cars or other objects, and they are doing this by using 3D laser scanning. So perhaps this might be interesting for the author of this work. Thank you.
Yes, of course. Actually, problem is that the funded amount was limited, so that's why we are having only choice to take a low-cost scanner. So we just take 2 scanners in that particular project, and definitely if we are having some more funding, so definitely 3D scanners are more better. So yes, this is true.
Okay.
Thank you. Thank you.
Thank you very much, Syed. Very interesting. If there is any more questions, you can address the author and information you can find in his paper. Thank you very much.
Thank you so much.
So next presentation is humidity and isopropyl alcohol detection sensor based on plastic optical fiber, delivered by Dr. Laurent Zolga from Technical University in Cluj-Napoca, Romania.
Thank you very much, Alberto. I will present my work, and I will start out with some motivation taking this journey to implement such a humidity sensor, and mainly to implement a system that can detect inflammable vapors. This work started out when we had a problem with the chemical faculty 3 years ago, when an explosion was happening because some inflammable vapors had get in contact with some sparks in the lab. So I started out to work on optical fibers. I worked first time on glass fibers, but from the literature we can observe that this type of sensors, temperature, humidity sensors, strain sensors using glass fibers are very expensive because of the interrogators that are used. Usually OSA, optical spectrum analyzers, are used, and they are very, very expensive to do this job. So the principle of operation of such a humidity sensor, it's based on exposure of the core of the fiber. In this case, I used the plastic optical fiber, which is very easy to handle, and mainly because of getting rid of the cladding of the fiber where the vapors can interact with the core of the fiber. What's happening? The critical angle of the fiber inside of the fiber between the core and the cladding will change. For example, when the light is passing through the core of the fiber, if we are changing the index of reflection of the outside medium, for example, from 145, 144 that we have for the cladding, and we are getting to 1.33 for the water droplet, the angle, the critical angle will start to decrease. Because it's decreasing, it means that more light rays which are getting in touch with the water droplets in this space will suffer total internal reflection, and we have more light on the infrared receiver. Because of this, we used infrared emitter and receiver in the 940 nanometer wavelength. We didn't want to have interaction with the ambient light. And now for the setup. To control the humidity, I created a box with the 30 centimeters length on each dimensions, and I distributed inside of this box electronic sensors, well-known electronic sensors like the DHT22. From the data sheet, they are capacitive humidity sensors. They can measure as well with the thermocouple the temperature inside of the box. And after these measurements, the fiber it's placed on top of the box, and we have two fibers. One is exposed, so it's the sensing fiber which is exposed. So a part of the cladding is stripped down to get interaction with the humidity, with the water vapors, and the other one it's a reference fiber which is not stripped. And it means that the water vapors cannot interact with the fiber. It means that the signal must be the same on that path. This is the practical implementation of the setup. On the left side, we have the electronic part with all the connections. And on the right side, we have the box where we control the humidity and for the fiber and the electronic sensors. The first task was to see how the DHT22 sensors are working in such a medium, because from the datasheet we have an accuracy of 2 to 5% accuracy of the measurements, and between 0 and 100% relative humidity. They can measure this range of humidity. The distribution of the sensors are on the left side, on the right side, and on the top of the box. We can see that two sensors are working good. So the left and the right side sensor are working well. The first test was done in the same, we didn't change the temperature, so we remained with the room temperature. And the humidity, we didn't introduce humidity in the box. So we wanted to have the same humidity from all the sensors. Because they have a small inaccuracy in the measurements, we can see that we have this data as well in my measurements. To control the whole setup, I did a software calibration of one of the sensors to use the same, to have the same room temperature and humidity in the constant medium for all the sensors. The next step for the measurements was done introducing humidity in the box, but controlling the humidifier 10 minutes on in on state, and after that 10 minutes in off state. As we can see, the red graph is for the top sensor. It means that it's reacting in a longer time because it's on the top, and the left and the right humidity sensors are reacting very quickly, being very close to the humidity source. The last test was done by controlling the humidifier in different steps between 2 seconds, 5 seconds, 10 seconds, and 20 seconds in on state, and after that leaving the setup to stabilize the humidity. In this case, we have 5 seconds on state. So here is the pulse for the humidifier for 5 seconds on state, and after that we have around 2 minutes to stabilize the humidity in the box. All around, the time spent from the pulse and to the end to the stabilization, it's around 2 minutes and 10 seconds. All these measurements done for 2 seconds, 5 seconds, 10 seconds, and 20 seconds on state for the humidifier were conducted in this table, and to show the steps, the accuracy of the jump steps. The best one is for 2 second on state. We have a jump step of 0.5 relative humidity jump step. And for the 5 second, we have 1.5% humidity jump. But the reaction time for the 5 second on state of the humidifier is much quicker than for that with the 2 seconds. All these measurements were done around 10 times. So they were repeated 10 times. So it's not only one measurement. I present only one of them. And this is what's happening when I switch on the humidifier for 5 seconds. And after that, leaving for around 2 minutes and 20 seconds to stabilize the humidity, we can see these jump steps for the humidity. So it's between 0.4 and almost 2%. So these are the jumps to have a well-controlled humidity in the box. And now let's see what's happening with the sensitivity of the POF fiber. In the case of the plastic optical fiber, we exposed, first time I exposed 1 centimeter of the core for the humidity, and the both fibers, so the reference fiber is the red one, and the blue one is the sensitivity fiber. We set up the input to have on the receiver around 3.03 volts. So this was the beginning of the first measurement. And after that, when the humidity increases, we can see that the voltage read by the sensor from the infrared sensor start to increase. Till we reach the maximum humidity, we have 3.25 volts on the receiver. This was the first test with the 1 centimeter exposed the fiber. The next one was with 2 centimeters of the fiber exposed to the humidity. As we can see, the reaction of the fiber, it's much quicker. We can see on this slope. So the reaction, it's much better in this case. And we tested out a third one. I tested out with this one with 3 centimeters exposure of the core. And it's very close to what's happening to the 2 centimeter exposure. So this was for the humidity test. And in the end, I compared all these parameters obtained for the POF and for the DHT humidity sensor in one table to see what are the values that are changing and the reaction times for the fiber and for the DHT sensor. From the reaction point of view, they are almost the same. So they react around 30 seconds for the reaction for the humidity. And for the output voltage, when it's for the humidity, for the POF humidity sensor, it goes up with the 0.2 volts when we reach the saturation. And now this setup, after that, I switched to a setup to detect what I was interested into isopropyl alcohol detection for a chemical lab, where they are using this type of solvents. And the first test was done in room temperature setup, where I didn't change the temperature. It was room temperature, and 50 milliliter isopropyl alcohol was introduced in the box. The reaction of the fiber started out after 8 minutes, and we have a small shift in the output voltage for the reaction fiber. So this was done in room temperature. What's happening when we start to increase the temperature? We can see till 55 degrees, we have the same change. After that, between 55 and 70 degrees, we have another change in the output voltage. But in the end, when we reach out after 70 degrees Celsius, the optical fiber start to melt down. So the temperature is too high, and in reaction with the isopropyl alcohol, it starts to melt. The sensitivity, let's say for the POF fiber for room temperature without alcohol, it can resist up to 120 degrees without being affected. But in reaction with the solvents like the isopropyl alcohol, the reaction of the fiber is very quick and it will be destroyed. So it means that we don't have communication length between the emitter and the receiver. So it means that we can detect such vapors. As a conclusion, from this experiment, a 2 centimeter fiber, its exposure of the core, it's more than enough to detect the humidity or alcohol vapors with such a sensor. About the reaction, in some cases we obtain with 12 seconds a better response than the DHT22 sensor, which is a simple one. It's a low-cost one. And another thing, it's that it can be it can be tested. This type of sensor can be tested with other solvents as well. So inflammable vapors as well, like let's say methylpropyl alcohol or other type of alcohols. Thank you very much for your attention. And if you have questions, please let me know, and I will be happy to answer to your questions.
Thank you very much, Laurent, and thank you for being according to schedule. It was very nice presentation. Is there any question from the audience here?
Alberto, very short question. Can I?
Yeah.
Yeah. Okay. I'm sorry. About what about the frequency, the wavelength of? You mentioned something about the wavelength of operation or the frequency of operation. What about if you could use other frequencies of operation or other possible modes for your interesting experiment?
Yes, I use it. I didn't mention it. Yes, it's a good question. I used it in a continuous wave. So in this setup, I used the emitter in continuous wave, so it was always on to have always a contact with the exposure of the fiber. So it means that being a multi-mode fiber, it means that a lot of light paths are interacting with that surface, and that's why I used not a laser. I used an infrared, an LED, because it's a broadband from the direction point of view. I have a lot of light rays which can interact with the external part of the fiber. So I didn't use the laser, and it's used in continuous wave to always have a real-time interaction on the receiver.
Thank you very much. Thank you.
Thank you too.
I have also a small question.
Yes, please.
I'm a little bit curious if this length of this open piece of the fiber is somehow related to this humidity level. So we see that now the saturation about a 2 centimeter piece. Yes, 3 centimeters already doesn't play a role. But guess if, for example, the humidity levels would be lower. Yes, maybe the different length could be, or it doesn't. The question is, does you check what is the relationship here?
Yes, I work on this relationship. I'm still working on this relationship. From the experiments that I presented you, it's I wanted to see how I wanted a quick response from the sensor, from the humidity point of view, and that's why I tried out 3 different lengths of exposure. I started out with 1 centimeter to see what's happening, and I observed that I have a very low response of the sensor. It was much lower than the DHT, than the electronic sensor. So it wasn't that length. It wasn't a proper one, because I wanted a much quicker response than the DHT sensor and the electronic sensor. After that, I switched to the 2 centimeter length, and I observed that it's better than the DHT22 sensor. And after that, I said, okay, let's see what's happening if I go up with a higher exposure, with a longer exposure. And of 3 centimeters, it's not better. It could be that because I already have losses on that length. So this one can be tested out analytically. Later, I work on this one to test it out analytically in a program to see what's happening on the size of the core, how the size of the core and of the exposure can influence the sensor. So I have two main parameters that can influence the sensor, definitely.
Okay, thank you. Because we have also some group doing in Riga with some optical, but they use mostly telecom fibers for the pressure measurements, and this optical sensors, by the way, have very great future. I believe this is very good.
Yes, they have a great future. They are widely used, but the main drawback for this moment, all of these sensors, it's the interrogators, because they are working on different principles. For example, Brion effect, Rehman effect. All these interferometer sensors they need optical spectrum analyzers. be sure where is the frequency, where do they react. And because of this, because the interrogators are very expensive, it's not affordable for everybody.
Yes, maybe, yes.
So this is the main drawback for these very good sensors.
Okay, thank you very much, Laurent. Thank you for your presentation. Thank you for the answer.
Thank you very much.
So we move to the next one, which is Pistivorous bird deterrent device based on a direct digital synthesis of acoustic signals. It is developed by Arturs Abotnis from the Institute of Radioelectronics from Riga Technical University. So Arturs, it is your turn when you want.
Okay, so I cannot share because it's already
Laurent, could you
shared.
please stop the sharing? Of
Yes, of course. Sorry. Yes.
Okay. Okay, this is. Okay. Hello, everyone. I'm Arturs Abotnis from Riga Technical University. So not very far from our Lithuanian colleagues. So unfortunately, this year we still are in pandemic. So, and I'm going to talk about our project about project of Pistivorous bird deterrent device based on direct digital synthesis of acoustic signals. So so this is seemingly, it could be, seems like a very simple problem. Just we have a birds and we are going to deter them, but it was a quite an interesting, we got some quite interesting result. So this research was funded by European Maritime and Fisheries Fund. And the objective was the development of system which deters birds from the fish ponds. And this is a part of this project. And this is acoustical part of this system. And in this part, we explored also such thing as a bird hearing and existing solutions to deterring birds from some places. And we create some algorithmic base for the sound generation and also got some implementation of this. And I'm going to talk about all these tasks. So where is the problem? Okay, let's go with the next. The problem is this, there are some birds which are in recent years, the population of some birds have rapidly increased. And one of these birds is this cormorants. Yes, this cormorant, the population of the cormorant is, here is a picture. This is a protected bird, which is not allowed to hunt. And this population of this bird is very rapidly increasing, especially in this European territory. And maybe for my European colleagues are already familiar with this problem. And these cormorant families are expanding. They are taking huge territories. And as you see, for example, from these pictures, they are like destroying areas around some water reservoirs. And very frequently, there are some artificial fish ponds where there are some fish growing inside going on. Then if this cormorants start to live at the coast, then there's usually it goes, this number of fishes here go down to zero, and they catch even all small fishes out. And this is a huge problem, by the way, and very huge losses from this problem. And there are, of course, some solutions to this problem. One of them is some typical things like this is called guns, yes, deterring guns, gas guns, where you can install this gas gun on the coast and you can deter, but most of the birds, I would say all of the birds, because cormorants are by far not the only birds living at the coast of all these water ponds. There's a lot of various species, and many of them are hunting, yes, and they get used to these devices. They even can predict these shots, and soon after this shot, they return back. It's also possible to use some nets also over the fish ponds, but if the territory is because many of these fish ponds are quite huge, they're hectare huge, and installation of the nets over such big reservoirs is quite problematic. And of course, people start to use some electronic devices. So you maybe are familiar with such kind of small deterring devices in some buildings when you are protecting not fish ponds but maybe some crops, and this is one of the way how to deter birds. Also, airports is also one very important area where these birds are big problem. In the airports, they use so-called the newest development for the airports. This is so-called this parametric arrays. Yes, this is this sonic shield, so-called. Yes, and they use many speakers which emit coherent acoustic waves, so that they produce some field with very big noise. And then in this case, the birds avoid this area because they cannot communicate with each other, and seems that communication between birds is very essential part of their life. And if they cannot communicate, they leave this area. But the drawback of this solution, it is extremely expensive because you need parametric nonlinear speakers. And this is affordable for the airports, but not for the fish ponds. Yes, okay. So what we can do in this acoustic deterring, yes? If we look to the hearing of the birds, they hear in quite a limited frequency range. Most of the birds are hearing like from 1 kilohertz until like in the air, this is 5-6 kilohertz. And so we must emit sound in this range. So some, for example, ultrasonic and so on are not efficient because there are devices claiming they are deterring birds in the ultrasonic range, but ultrasonic doesn't work in the air. If we look to those species of the birds which are hunting underwater, because this is the problem with the fish ponds, the hearing of those cormorants, this is the red line here, goes until also like 10 kilohertz. But there are some species able to listen unto 100 kilohertz underwater. Yes, this is very interesting how it works. Yes. So, and what we decided to do, we developed some equipment which is deterring birds or in the air and also underwater. And there was a problem with bird habituation to the sound. If we play some recorded sounds, they get habituated very quickly. So it doesn't work at all. And the problem was to get some synthesizer which synthesize sounds which change all the time or variate at least. And the idea was to synthesize some sounds of these predator birds. Yes, and so this is an ambitious task to synthesize biological sounds. And we look to some methods here, what we can use. This pulse code modulation, this is just direct recording of the sound. This is not very efficient because you cannot easily modify the sound. You can play the same. This is very easy. You just put the player, but gets habituated, or you have to have huge library. This is a wavetable synthesis, classical method when you use some pre-recorded simple sounds. It comes from the music industry. And one of the most interesting methods is a frequency modulation synthesis. It's frequency modulation synthesis when you use one wave which modulates other. For example, one sinusoid modulating another sinusoid. And if the frequencies are close to each other, yes, then you can get very interesting effects. And this effect was noticed by this Mr. Chowning in '73, who developed this FM synthesizer, which was later commercialized by Yamaha, and it was extremely popular musical synthesizer. This was done at this university get a lot of money from this patent. From this, it was not patent, it was some agreement about use of this development. And there is of course, some ways of simpler ways to synthesize. This is so-called direct digital synthesis, which is used in many frequency synthesizers, also for radio communications and so on. In this case, you change the frequency quite slowly, so the modulating frequency is much lower than the carrier, and in this case we can say this is very large modulation indexes, and there's no such much interesting effects, but you can easily control the synthesizer. And of course there is a multi-tone DDS. In this case you can synthesize various sounds including voice and so on, but it becomes quite complicated as well. So what we decided to use this simple DDS, direct digital synthesis, in this case, because of the availability of devices which do this. Namely, it was this analog devices AD9850, which is quite popular synthesizer working up to 30 megahertz, yes. And we controlled this chip, in what it was a board, in fact, which we used with some specific microcontroller program. We developed some protocol for the storing sounds, which are able to control this duration of the segment, frequency, amplitude, with some resolution. And in this way, we was able to synthesize many birds songs, yes, and quite similarly to the natural ones, with very compact design and very few much lower memory use, yes, because you use, this is like we just store the sequences but not the samples of the sound. And this is there is some problem, because if we wish to synthesize natural sounds, we have to convert some PCM records of the existing sounds. So we developed some algorithm in which we convert PCM sounds, recorded sounds, which are quite noisy sometimes, to this synthesized sequences. And if the sound, many birds has this one major frequency in the song, so it is easy convert. But some birds have two, for example, and in this case, this method has a difficulties, and we have to use some filtering to avoid jumping between two frequencies. It was like a little bit funny when you hear it when it jumps between two.
So, sorry, we have 2 minutes.
Okay, yes, I will finish. This is an algorithm. Here we read audio file, calculate spectrogram. From the spectrogram, we calculate the maximum frequency. And by the way, this method is I think for you looks quite straightforward. Here the hints are dealing with the noise. The noising of the signal is the most difficult part. And then we created those sequences. And here is a picture how it looked at the end. It was a ready board with this AD9850 on the larger board. Yes, it's this part. It has several other microcontrollers for the some other tasks. And the final look of the systems. This is here. This is a ground-based system with a speaker, also the laser, because this is optical complement for this system, and also floating system, which is acoustic over in air and also underwater speakers at the bottom of this device. The results show that it works. However, without the optical part, it is not that efficient. Yes, this optical part is very important. Yes, by the way. And but anyway, we developed some technology for the sound generation, and we can generate biologically relevant sounds and synthetic sounds, and we can join with some smarter systems in the future and have like maybe some kind of very adaptive and intelligent sound generation. And we could prevent the habituation of those birds. So thank you very much.
Okay, Artur, thank you very much for your presentation. So we have time for a very fast question, if any. Is there any question from the audience? Okay. Well, thank you very much again. Sorry, I will go to the next one because I would like to keep in the schedule. Okay. Thank you, Artur. Very interesting. Thank you very much. Okay, so the next one is going to be efficient feature set development for acoustic gunshot detection in open space. And presenter is going to be Milan Sigmund. So Artur, if you could, thank you. Milan Sigmund, hello and welcome. And when you're ready, you can start. Thank you very much. No, Milan. I'm afraid we cannot hear you. Can you hear us? Sorry, Milan, we cannot hear you.
Maybe it is better to go with next presentation, and Milan will solve his microphone issue.
Yes, sorry, Milan. We're going to pass to the next presentation, if you don't mind, and then we will get back to yours once we solve this problem. Okay, so next one, if you're ready, Shindong, are you there?
Yeah, I'm here.
Okay, thank you very much. So next one is going to be advanced calculation model for V-belt temperature field, and it's going to be presented by Shindong Ni. Okay, so Shindong, whenever you're ready.
Yep, I'm ready. So let's give him some time. And can you see my screen?
Yeah.
Okay. Okay, hello everyone. Thank you for your time listening my report, and it's my great honor to give a presentation here. And my name is Ni Xindong. I'm a PhD student from China Agricultural University. So let's begin the presentation. And my topic is advanced calculation model of V-belt temperature field. And I will expound my research as the following 5 parts. So as we know, most of transmission on the combined harvester is realized by belt transmission. So V-belt is the most crucial part of power transmission. However, in the process of continuous high-strength operation, surfing hardening, grid hole fracture, and other features are appeared on V-belt due to the temperature rise, which seriously affects service life of belt and stability of the whole machine. Therefore, research on the temperature field of V-belt is of great significance to improve its service life. In the process of summary and analysis, it is found that there is a strong correlation between dynamic heat and the power loss of belt drive. At present, existing research is mainly focused on the theoretical modeling and the experimental optimization method of power loss of FEAD system. FEAD is from an engine accessory drive. Well, there are few reports about the calculation of temperature field. Therefore, based on the calculation of V-belt power loss, we establish an advanced calculation model of V-belt temperature field through finite element calculation and experimental verification. So before calculating the temperature field of V-belt, heat source...
Teď to funguje. Jsme špatný vstup zapli. Máte tam hodně těch direk vzadu, tak to prostě píchlo na jinou.
Milan, we can hear you now. Okay, thank you very much. Okay, Ni, you can keep.
Okay. So before calculating the temperature field of V-belt, heat source of temperature rise must be analyzed and quantified. It can be seen from the relevant literature that heat source of the temperature rise of V-belt come from internal friction and the external friction. The internal friction heat source is caused by hysteresis response of rubber. Among them, dynamic bending is the main component of internal friction heat source. During load transfer process, V-belt is periodically ruled in and out of pulleys. Because of limitation of pulley geometry, V-belt will be bent and spread periodically, which will cause dynamic bending of V-belt to generate heat. Well, external friction is caused by the elastic sliding of the belt on the sliding arc. So after determining heat source of temperature rise, then the next step is to quantify the heat source value. In this paper, dynamic analysis software AVL-XITD is used to complete modeling, simulation analysis, and power loss calculation of V-belt drive system. It mainly consists of four steps. The first step is to set the physical parameters of pulley and belt. The next step is to set the parameter of tensioning mechanism. And the third step is to set the drive speed and load. And finally, we can calculate the heat source value of specific conditions. In our research, a V-belt drive system harvester is taken as the research object to calculate temperature field of V-belt. Calculation model of temperature rise and heat source based on AVL-XITD is shown in the red picture. This picture. So in order to explore the heat source calculation results and the rules of V-belt under different conditions, we chose 10 different conditions to conduct comparison. In the change of working condition 1 to 5 is the speed of driving pulley, while the change of working conditions 6 to 10 is driven with load. When the driving pulley speed is a single test variable, heat source calculation results are shown in the left picture. It can be seen from the results that most of heat sources of V-belt come from internal friction, and the proportion increases with the increase of driving speed. Because bending frequency of V-belt increases with the rotation speed of driving pulley, which causes the hysteresis heat of the rubber to increase. When the load of driven pulley 2 is a single test variable, heat source calculation results are shown in the red picture. It can be obtained from calculation results that although the internal friction accounts for a larger proportion of total heat source, The proportion of external friction heat source gradually increases as the load torque of driven pulley 2. Now, after obtaining heating source calculation value according to energy conservation equation and Fourier heat conduction law, the balanced equation in steady state can be listed, where alpha is heat flow distribution coefficient between V-belt and pulleys. PFN is total external friction heat source between V-belt and pulleys. pH is internal friction heat source value of V-belt. ABR is contact area between outer surface of V-belt and air. HB is equivalent thermal convection coefficient of V-belt. TB is steady state temperature value of V-belt. TA is reference temperature. In three-dimensional dynamic heat transfer model, bending internal heat source acts on V-belt in the form of body load, and the external heat source acts on sliding contact surface in the form of surface load. In order to reduce the amount of calculation and improve simulation efficiency, three-dimensional dynamic heat transfer model is equivalent to two-dimensional static. The internal heat source body load is converted into a surface load, and the external friction surface load is converted into a linear load. Then the temperature field is solved by finite element method after meshing and calculation. The results show that the temperature of V-belt increases gradually and tend to be stable with the increase of driving pulley speed or load torque. In order to verify the temperature field calculation model of V-belt, the setup composed of transmission system and the measurement and control system are developed. The measurement device mainly includes Hall speed sensor, non-contact infrared temperature sensor, and the torque sensor. Hall speed sensor is used to measure speed of driving pulley. Non-contact infrared temperature sensor is used to measure temperature of V-belt under different working conditions. Torque sensor is used to obtain the load torque on driven pulley 2. The control equipment mainly includes frequency converter and the magnetic powder brake. Frequency converter is used to control angular velocity of driven pulley. Braking torque is applied to driven pulley 2 by means of a magnetic powder brake. The braking torque of magnetic powder brake is regulated by a controllable power supply. Motor controller and the controllable power supply are connected to CAN bars through serial port to CAN module. Data measured by Hall sensors, infrared sensor, and torque sensor are processed in microprocessors to be converted into digital data. And data from CAN bars is transferred to computer using a data acquisition software developed by LabVIEW. And the experiments are conducted in the indoor environment with 16.2 ambient temperature and 18.4 relative humidity. Compared with the simulation results, temperature rise trend of V-belt is consistent. From the beginning, the temperature of V-belt increases rapidly, then increases slowly, and finally tends to be stable at the same speed level or torque level. At different speed levels or torque levels, the steady state temperature value of V-belt becomes larger as the speed increases. This phenomenon can be explained that from perspective of heat generation and heat dissipation of transmission belt. At the beginning of the test, convective heat transfer between belt and air is small, and most of heat sources are used to increase the internal energy of the belt. Therefore, the belt temperature rises fast. In unsteady state process, with the increase of temperature of belt, the convective heat transfer intensity between belt and air gradually increases. The heat source value used to increase internal energy of belt gradually decreases, and the temperature rise rate of belt gradually decreases. In steady state process, the total heat source value of belt is equal to convective heat transfer value between belt and air. Internal energy of belt doesn't change. The temperature of belt doesn't change either. So in order to evaluate the accuracy of simulation model, third T is set as the comparison in this paper. In any case, third T first increases, then decreases, and finally stabilizes. The whole process can be divided into two stages, unstable process and stable process. It is an unsteady process in the range of 0 to 475 seconds. In this process, the maximum value of third T is 3.43 when driving speed is a single variable. Well, the maximum value of third T is 4.77 when the load torque is a single variable. After 475 seconds, there is a steady state process. In this process, third T tends to be stable. We can find that the difference between calculated value and the experimental value in unsteady state process is larger than that in steady state process. This is because only the heat flux distribution of friction heat between belt and balls are considered in the simulation of unsteady state process. And the influence of heat conduction between belt and pulleys are ignored. After heat flux distribution calculation, 93.4% of external friction heat is used to increase the internal energy of pulleys. And the specific...
we have 2 minutes to go.
Okay. Oh, sorry. The 90.4 of external friction heat is used to increase the internal energy of pulleys, and the specific heat capacity of pulley is 3.7 times of that of the belt. This will cause the pulley to have a higher temperature value than belt. Due to temperature difference between belt and pulleys, some of that will flow from pulleys into the belt. Therefore, in the unsteady process, test temperature will be higher than simulation temperature. And sorry for too many time. And here are the conclusion. And thank you for listening. And if you have any problems, just email us.
No, we still have time for. If you want to finish with the conclusion, we have a minute. But if there is any question for me from the audience. Any question?
I have a small question, maybe.
Yeah. Okay. Yeah.
I'm not a big specialist in mechanics, but now it seems like temperature will increase until infinity. Yes, but or not? How it was in this model? Yes, I do not see the temperature saturation. It's at some moment, no? Or I missed it because this delta T was always positive, no?
Mm-hmm.
In this, no, maybe go to the previous slide. Oh no, this. No. Where is the plot? Next one.
The police?
No. The next slide.
Oh, next slide. Okay.
No, the next. Where is a plot?
The next one.
Graphs. Okay, graphs. Is a temperature.
Temperature.
Mm-hmm. No, it's temperature from time. It was some plot here and looked like. Could you please show the next slide? Maybe there is not numbers. This one, yes. It seems like temperature goes up all the time.
Yeah. But after the temperature will increase rapidly first, and increase slowly, and it will tend to be stable here.
Yes, maybe it's some while become flat, because now it looks like it will increase.
In this picture, it likes always increase.
Okay, thank you.
Okay, thank you very much. Thank you for your presentation and the questions. So we're going to move to the last one, which is efficient features development for acoustic gunshot detection in open space by Milan Sikmuk. So Milan, whenever you're ready, you have 13 minutes and then 2 minutes for questions. Okay, thank you very much.
Okay. Good morning. Can you hear me?
Yes.
Yeah.
No, you just have to go to the PowerPoint you have in the background. This one, yes.
Okay. I will start it. So my presentation deals with gunshot detection in open space. The presentation is divided into slides. We start with introduction, then some short characterization of gunshot sound signals, our principle of gunshots detection, then the two sets which we use. They are optimized Gapster coefficients and time domain based feature set. And follows slide with evaluation criteria and achieved results. And finally, brief conclusions. In the field of gunshot detection, there are many systems, commercial systems for use in military and for urban and in-building application. Our work and development is focused on different situation. The motivation of our work was collaboration with international association named Safe Elephants. They are elephant herd in Africa equipped with special collars with GPS module to track the movement of the elephants. And our idea is to complement the collars with a special gunshot detection module that can send an alarm signal together along with location information. And in such a case, the game ranger can very promptly act. The basic characterization of gunshot sound signal is that they are impulsive signal with very high intensity, around 160 decibel, and with a short duration. This is mainly, in most cases, shorter than 10 milliseconds. We can see left typical gunshot signal in a time domain and spectrum of this signal. The waveform consists of two parts. The initial part is typical has typical an N wave with symmetric oscillation, and the second part is the decreasing oscillations. In spectrum can be seen some local peaks in the range 0 to 2 kilohertz, and the main frequency components are between 250 and 450 hertz. The basic principle of gunshot detection is as follows. First step, the amplitude is normalized in range from -1 to +1. Then the signal is segmented into short frames, usually 10 milliseconds, with overlap 50%. And we use a combination of two feature sets, linear frequency Cepstral coefficients and time domain based feature. These feature sets are fuzzied, and the next step is recognition or classification. We use neural network consisted or structured in two hidden layers of 20 neurons each. In the training stage was used 600 gunshots and 6 times 600 non-gunshots, and in testing 700 gunshots and 6 times 3,200 non-gunshots. The sum of non-gunshots or the sounds is divided in 6 categories. This is the means, while I write here 6 times 600 or 6 times 3,200. The first set of coefficients are optimized Cepstral coefficient. The block diagram in the left shows the calculation approach. Input is audio signals, then is the segmentation or framing, short-term fast Fourier transformation, and the next block is the linear filter bank. This block is the core of our optimization. We use gamma tone filter form, linear spacing of these filters in the range 0 to 16 kilohertz, and this frequency range is divided in 31 bands or filters, and we calculate 18 coefficients. The formula for calculation can be seen in the bottom left. The figure right shows the complete, the entire filter bank. The second group or set of features are shooting specific features. We use the time interval T between two dominant peaks, between the positive and negative peak. Area P, this area is bounded by the peak-to-peak curve and the horizontal axis. Then area A, this can be seen here. This is the area between the positive curve and horizontal axis with the duration 6 milliseconds, and similar is the negative area B, and the last feature in this set is the ratio of areas A and B. In the evaluation, we use two metrics. There are typical or frequently used metrics in binary classification. They are true positive rate and true negative rate. The equation for the calculation can be seen in the left part, where TP is number of true positives, that is when gunshots are identified as gunshots. Tn is number of true negatives. Non-gunshots are identified as non-gunshots. FP, a number of false positive. It is this situation, or this number of cases, is known as also as fault alarm. In this case, non-gunshots are identified as gunshots. And the last, Phi-n, number of false negatives. In this case, the gunshots are missed. The results, first, we have compared only the set of linear frequency Krebsstrahl coefficient with other Krebsstrahl coefficient, Mel frequency Krebsstrahl coefficient. This kind of coefficient is very popular generally for recognition and detection of audio signals. The optimized number of MFCC coefficient was 12, and the frequency range 0 to 22 kilohertz. And in the case of linear frequency coefficients, a group of 18 coefficients and frequency range 0 to 16 kilohertz. We can see in this table that the LFCC gives better results in both categories. And the second table shows separate results of true positive rate and true negative rate for LFCC, for the second group TDF, and then fused both feature sets as in single neural network and in ensemble neural network. The best results are slightly above 95% true positive rate and 98% of true negative rate. In the test, we have used.
Sorry, Milan, we have 1 minute and a half, 1 minute, 30 seconds, okay?
Okay. We have used it various hunting weapons in 6 different classes of non-gunshot sounds. These 6 classes are barking dog, sound from elephants, sound from rain and storm, car horn, engine sound, and human sound, including short shouts. And the conclusion, comparing to other methods, they are based on monochannel signals. We are slightly below the absolute maximum that was published, but the good advantage of our method is that 98% of environmental sounds was ignored. And from the point of implementation, we use a relative simple neural network. So thank you for your attention.
Okay, thank you very much, Dr. Simon. Is there any question from the audience? Any question? Nothing? Just, okay, thank you very much. I'm sorry, but the next session starts in 20 minutes, so I think it is better to stop now. So you can have a small break for the next session. Okay, thank you very much for all the presenters. And thank you very much for the audience, for your attention and for coming.
Thank you, Mr. Chairman, for chairing.
You're welcome.
Thank you very much. Thank you very much. This is very good. Thank you.
Thank you,
Thank you, Alberto.
Thank you.
Let's keep in touch.
Okay.
Okay. Lodek, nice to see you.
Have a nice day. Alberto, let's keep in touch.
Yes.
Best wishes. Yeah. Nice to meet you. See you later.
Nice to meet you. Nice to see you too.